Hello guys, welcome back to ptet.chemistry channel. So in this tutorial video, in fact it's a tutorial, not a lecture, tutorial video, because I'm going through this work 2. This is part of the work that is given to the 5070 year 9 chemistry students. As part of stoichiometry, you would have seen me covering in the lecture tutorials on empirical and molecular formula. So this work essentially is an extension of that lecture tutorial. So it's an application of those concepts which we would have learned and found out before. So this is on empirical and molecular formula. So before we do that, it's good to recap what empirical formula actually mean. Empirical formula refers to the simplest ratio of atoms, and that is very, very important in terms of how we will apply it across the different setting. Whereas molecular formula refers to the actual number of atoms. So you could have an actual number of atoms that could be simplified further. So that is when your empirical could be different from your molecular formula. So actual number of atoms in one single molecule. So that means you can only get molecular formula for simple covalent molecule, because only simple covalent molecule can exist as individual discrete single molecule. Things such as graphite or diamond or silicon dioxide, all of which are giant covalent molecules, or we will say they have giant molecular structure or giant covalent structure. Silicon dioxide, diamond, graphite, they all have an empirical formula, but they do not have the molecular formula because they do not exist as one single molecule. Everything else that exists as that has simple molecular structure or simple covalent structure, that means they exist as individual single molecule. They can have molecular formula which could be simplified further in terms of the ratio of atoms. They will give you the empirical formula. Sometimes they are the same, sometimes they are not the same. Alright? So without further ado, let's get started with this tutorial. So we have anhydrous. Anhydrous means not hydrated. It will make more sense perhaps by the next 2 lecture tutorial, I think. Aluminium chloride. So it contains aluminium as well as chlorine. So it has aluminium, it also has chlorine. So anhydrous means there is no water, not hydrated, no water. So it's just aluminium and chlorine. This is 20.2% by mass. Alright, so that means out of 100%, 20.2% is aluminium. If you have 100 gram of AlCl3, 20.2 gram would be the mass of aluminium, because it's percentage by mass. So I could set up my imaginary table like this. I do not need to draw lines, but I need to keep my work neat and tidy as well as level. So I will start by mass per 100 gram. Because I don't work with percentage, I use the percentage and convert it to mass per 100 gram. Why is it per 100 gram? Because it's in percentage. Percentage is out of 100. So this is 20.2 gram. Alright, so out of 100 gram, the percentage by mass is 20.2. So that means the rest of them is just chlorine atom. Be careful, we are comparing the simplest ratio of atoms because they want empirical formula. This goes back to your definition of empirical formula. You do not compare atom with molecule because it's atoms and atom for the simplest ratio of atoms. So it's out of 100 gram minus 20.2 because there's only 2 elements in it. There's aluminium and there's chlorine. 100 minus 20.2, I get 79.8. This is gram. So out of 100%, out of 100 gram, this is the percentage by mass. Next one, I need the mole. So the mole is going to be the mass over the relative atomic mass, mass over AR. So if you look at periodic table, the relative atomic mass of aluminium is 27, and then the next one, 79.8, is for chlorine atom. So the relative atomic mass for chlorine is 35.5. So mole is something that you will learn more and more, especially by the next couple of lecture tutorials. But as I've done during the empirical and molecular formula lessons, basically to introduce the idea of mole equal to mass over relative atomic mass for elements. Okay. We use 35.5 because we only have per atom. This is the relative atomic mass for one individual atom. Press that into your calculator. So 20.2 divided by 27. We get a lot of decimals. So 748. 79.8 divided by 35.5. I get 2.25 like that. So in terms of the simplest ratio, so we need to try and simplify that now. So I try to create a bit more space for myself so that I can write everything down there. Let me change the color. So I want the simplest ratio. If you want the simplest ratio, you compare the two mole, which one is smaller. So 0.748 is smaller, so you divide by itself. You divide by itself is just 1, and that one divide by 0.748. Press that into your calculator. 2.25 divided by 0.748. I get 3.01, which again, there's roughly 3, and therefore your empirical formula is just equal to 1 aluminium, the simplest ratio of atoms, 1 aluminium and 3 chlorine to the nearest whole number, obviously, because these are whole numbers. On to the next one. So we have a sample of anhydrous aluminium chloride. It has a mass of 2.34 gram. And this sample consists of this much mole. We want the relative molecular mass and therefore the molecular formula for the anhydrous aluminium chloride. So now you have a sample of it. So we need to use the data. So mole is equal to mass over mR. This relative molecular mass is mR. It has its own definition. So AR versus mR, these are stated in the syllabus and you need to know how to define them as per the syllabus. Okay, so these are both required by the syllabus. These are basic definitions. You should keep a book of your definitions, of all the definitions that Cambridge require you to be able to state, because if you can't do definition, it's very likely that you can't apply those concepts very, very well. Okay, so we have a mass and we have the mole, so we can calculate the mR. We rearrange our equation, we move the mR up there, and then we can move the mole down there. So this is essentially just cross multiply. So putting in the values, so your mass is 2.34 gram for the aluminium chloride, and the mole of the aluminium chloride, the anhydrous aluminium chloride, is that. So as you could see, mR has a unit of gram per mole because it's basically telling you the mass for 1 mole of the substance. And I get mR is 267.1. If you think about the data given is 1, 2, 3 significant figure. 1, 2, 3 significant figure. The 0 in front of the first number, which is not 0, is all not considered as significant figure. So you count this as the first, the second, and the third. So 1, 2, 3 significant figure, 3 significant figure. So I should really put my final answer to the appropriate number of significant figure. Okay, so that is just 267. I'm pretty sure they won't penalize you for forgetting the units, but you should know the unit of relative molecular mass by right. Without the relative, the molecular mass is gram per mole, but relative molecular mass is a ratio of mass. That's why relative mass does not have a unit, but this is molecular mass. Usually we think of it as mR has a unit of gram per mole. Now I want the molecular formula, and I had the empirical formula. So the way we would do empirical formula was before, and how we find out molecular formula basically mean how many of these simplest ratio of atoms, how many of these do we have. All right, so the mR of that will be the whole molecule. In one single molecule, what is the actual number of atoms? Molecular formula tells you the actual number of atoms in one single molecule. So in one single molecule, the actual number of atoms give you the mass of 267. So there's n multiple of the empirical formula. So I will have the molecular mass, relative atomic mass of aluminium. So how many of these aluminium I have? Aluminium, I have 1 of it. So it's 27 times 1 plus 35.5, the relative atomic mass for 1 chlorine. And I have 3 of them in AlCl3. Plus the 27 multiplied by how many times I need to multiply them. So inside the bracket, I get 133.5 multiplied by n equal to 267. So n equal to 267 over 133.5, that is equal to 2. So what does this tell me? This tells me that the empirical formula multiplied by 2, I will get Al2Cl6. Al2Cl6 is the empirical formula for whatever they want us to do here. For this anhydrous aluminum chloride, is the actual number of atoms. Of course, 2:6 can be simplified. The simplest ratio of the atoms in the compound give you the empirical formula. So both empirical and molecular formula are definitions required by Cambridge, just like Cambridge also require you to know the definition of relative atomic mass and relative molecular mass. So make sure you know each and every one of these. Question 2, so this is also a question of empirical and molecular formula. So here we have carbon, hydrogen, and oxygen. Just now we had 3 elements. Now we have, just now we had aluminium and chlorine, only 2 elements. Now we have 3 elements. I give you the percentage of carbon. I give you the percentage by mass of hydrogen. So I have carbon atom, hydrogen atom, oxygen atom, because empirical formula is the simplest ratio of atoms. So I always label. They give us percentage by mass. So I label mass per 100 gram. So it's 57.1 gram. It's 4.8 gram. Out of 100%, out of 100 gram, the percentage by mass of oxygen is going to be the difference, 100 minus 57.1 minus 4.8. It's like you had 3 slices of cake, one of which is this much, one of which is this much. The remaining slice would have this much amount by taking the difference. You could be thinking about it as 100 minus 57.1 plus 4.8 is the same thing. Minus and plus give you minus. Minus and plus give you minus. So they are the exact same thing. It's just mathematics. And if we are very careless with mathematics, then you need to be very careful, because these things can cost you a lot. Okay. So I want the mole. The mole is going to be the mass. Mole equal to mass over mr. In this case is AR, because you don't have a molecule, you have atom. So it's called relative atomic mass, definition of which we did in atomic structure in the last 2-3 topics. So you can go back to those lecture tutorials and have a look at what we discussed before. Divided by 12, that's the relative atomic mass given in the periodic table. So 4.8 over 1, because there's the relative atomic mass of hydrogen atom, not molecule. Empirical formula, simplest ratio of atoms. So that's why we talk about atoms, and therefore we use 16 for oxygen. And if you put it into your calculator, then hopefully you will get 4.76, and there's 4.8 and 38.1 divided by 16, I get 2.38. Now looking at these 3, these are mole. So the simplest ratio, so I'm running out of space here, but let me see if I can squeeze it all the way up there. I might move this a little bit to the right. So in the real thing, you don't have the chance to actually move stuff around, so you need to be careful, and therefore you need to make full use of your space. Alright, so I really need the space, because I'm going to do the next step, which is to do with simplest ratio of the atoms, the mole ratio of the atoms. This is the smallest number, so it's going to be 2.38 over 2.38, which give me 1. 4.76 over 2.38, and you will get 4.76 divided by 2.38. I get 2 exactly. In 4.8 over 2.38, there will not be 2. But they will be very close to 2 as well, as I suspect. So there's 2.02. You give it to the nearest whole number. So what we have then is C2, because there are 2 carbon. There's 2 hydrogen, so H2 and O. So the empirical formula is going to be C2 H2O. On to the next one. So this looks a bit tricky. We do need to know how to calculate mole. Okay, so in hindsight, this should have been questions that are given after you have done mole concept. So this is volume in cm cube. This is a solution. A solution will have concentration. Because a solution is dissolved in water, the mole per dm cube means how many mole of KOH is dissolved in 1 dm cube of water. This is per dm cube of distilled water or deionized water. So it's basically distilled or deionized water. What we have then is we need to try and think about these. If we first work out the mole of KOH can be expressed in this form. Small n bracket the substance, it means the mole of KOH. Okay, mole of KOH is equal to volume. This is mole per dm cube, this is concentration. So if I follow the units, so this is mole per dm cube. How do you get to mole? This is mole per dm cube. I need to multiply by volume because this is over dm cube. I need to multiply this by volume. The volume, you need to convert it to dm cube, so I can divide by 1,000. If you do maths, eventually you will see that 1 over 1,000 is 10 to the power minus 3. So 18.5 cm cube is also equal to 18.5 over 1,000 dm cube. Because of this conversion factor, 1 dm cube is 1,000 cm cube. So dm cube means decimeter cube because 1 dm is equal to 10 cm. And if you do maths and physics, 1 decimeter is 10 cm. If you cube on the left, you also cube on the right. 1 cube is 1, dm cube is dm cube. 10 cube give you 30, which is 1,000. cm cube give you cm cube. 1 dm cube is 1,000 cm cube. This is a conversion factor that you must know. And I could also write this as 18.5 times 10 to the minus 3 dm cube. It means the exact same thing. So sometimes you'll see me writing this in terms of over 1,000. That means I convert the cm cube to dm cube. I could also do 18.5 times 10 to the minus 3 dm cube because you could do that very easily on your calculator. So press that into your calculator. 0.250 times 18.5 divided by 1,000. Then you get 4.625 times 10 to the power minus 3 mole. Okay. What else can I say? 1 mole of W reacts with 3 moles of KOH. 1 mole of W reacts with 3 mole of KOH. So the mole of W is to the mole of KOH. So we're talking about mole. This is whatever they're given us. So 1 mole of W. This could be the other way around. You are following what you write them down. If you got it the other way around, your 1 will be at the bottom because the one on top means the mole of W. 1 mole of W reacts with 3 mole of KOH. These are the mole ratio given to us in terms of mole. This is actual. So the actual mole of KOH, I'll put down at the bottom. So 4.625 times 10 to the minus 3 mole. So this is the actual mole of W. So there you go, you get your actual mole of W. You just bring this up there. This is cross multiply, bring all of this up there. So it's this times 1 over 3. So you get 4.625 times 10 to the minus 3 times 1 over 3 is essentially that number divided by 3. But that is not our final answer. They want something called relative formula mass. Relative formula mass is another name for relative molecular mass. It's just that molecular refers to molecule, formula refers to things which are not molecular, things like ionic compound. Anyway, we've gotten the mole of W. Now we've gotten the actual mass of W. Then we can find the MR of W because what do we need to do? Mole is equal to mass over MR. So the MR is going to be mass over mole. So you have mass 0.194. So there's 0.194. And then you divide that by mole, which is all that thing there. So 0.194 divided by your answer. And you convert it to, you see the data there, there is 3 significant figures. 1, 2, and 3 significant figure was something you have done in lower secondary mathematics. 1, 2, and 3 significant figure, 1, 2, and 3 significant figure, 1, 2, and 3 significant figure. So what is appropriate? Your calculator show you a bunch of numbers. You need to convert it to the appropriate number of significant figure based on your data. Based on your data, you cannot get higher significant figure more than what you started with. I get 125.8. So 125.8 is not 3 significant figure. It's blah 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 blah. 1, 2, and 3. I want my final answer to 3 significant figure. So I look at the next one. This is more than 5. Therefore, I add 1 to it. I get 126. Okay. So what else do I know? I know the empirical formula is C2H2O. The empirical formula is C2H2O. And this is empirical formula. And empirical formula, how many multiple of it is going to be equal to the molecular formula. So I want to total up the molecular mass, which is going to give me the relative formula mass or the relative molecular mass of 126. So I have N multiplied by a whole big bracket. I have 2 carbon, so 2 times 12, 2 carbon, because this is the mass, relative atomic mass for 1 carbon. And then 2 hydrogen, 2 times 1. 1 times 16 for the oxygen, so whatever is in the bracket, they give me 24 plus 2 plus 16, so there's 42N is equal to 126. Remember, N here is not number or mole. Perhaps I should use X or Y. Perhaps I should change this to X or Y so that you're not confused between what is number or mole and what is not. But you should be very clear on what this X represents, or if I use N, what this N actually represents. All right. So let's just divide by 42, and you should hopefully get 3. It means how many multiples of the empirical formula will give me the molecular formula that has the mass of this. So the molecular formula is, well, the empirical formula. How many multiple of it? 3 of them, because X is equal to 3. That means C6H6O3. 2 times 3 is 6, 2 times 3 is 6, 1 times 3 is 3, so I get C6H6O3. Okay? Alright, so moving on to the next question. So we have this compound A. It's an organic compound again. It contains carbon, hydrogen, and oxygen. So this is a slightly difficult question because you pass this vapor of A, vapor meaning gas, you pass it over a large quantity of heated copper 2 oxide. You get it completely oxidized, so you haven't really done this chemistry yet, and you will know more about this, what oxidation means, perhaps by the end of the year, in about half a year time, I guess. Carbon dioxide, you know, CO2. Water, you know, H2O. The product are collected, and you found out that you have this much carbon dioxide, this much water. Now, what did you add? You added copper 2 oxide. Copper 2 oxide has no carbon, has no hydrogen. So all the carbon here come from A. All the carbon from A, because the copper 2 oxide does not, copper 2 plus or 2 minus, copper 2 oxide does not contain carbon at all. It contains copper and oxygen. So all the hydrogen is from A. So this is analysis. You're trying to work out how much carbon is present here. They did specify in bold 3 decimal place, not 3 significant figure, 3 decimal place. This is 1 decimal place, 2 decimal place, 3 decimal place. After the decimal place is 1, 2, and 3 decimal place. They want the mass of carbon atoms. They don't say it, but they mean atoms. Okay, so the mass of carbon atoms, it means out of 352 grams, out of 0.352 gram, how much of it is carbon? So this is expressed in terms of the molecular mass. The molecular mass of CO2 is 12 times 1 plus 16 times 2. Press into your calculator, you get 44. Out of 44, how many are carbon? You have 1 carbon because they don't show you the 1 there. So it's just 12 times 1. Out of the 44, you have 1 carbon, the mass of which is 12. So 12 out of 44 times the total mass of the carbon dioxide. And you will get 0.096 on your calculator, and that shouldn't be the answer that you put down, especially if you know what 3 decimal places mean. You will know to follow instruction. Okay, so there is 3 decimal place there. I just added a 0 at the end. Oops, nope, sorry. This would be 3 significant figure. I was talking rubbish, obviously. So this is 1 decimal place, 2 decimal place, 3 decimal place. So that is actually correct, 3 decimal place. Okay. Now you want the moles of carbon atoms. That's why I work out the mass of carbon atoms. And therefore the mole, so the mole of carbon atoms, I better write down the mole bracket carbon atoms, is going to be the mass over the molecular mass, or atomic mass actually, because these are atoms. So divided by 12, I get 8 times 10 to the minus 3. This is what your calculator show you, and this will be the one that's wrong because you want your answer to 3 decimal place. So ideally I need to show it to 8.000, 8.000, because that is 1, 2, and 3 decimal place, times 10 to the minus 3. If you don't like that, then you can express it in terms of the real deal, which is if you don't like that expression, you can express it to 0.008. This is also 3 decimal place. Okay, so 1, 2, and 3, or you can do 1, 2, and 3. It's up to you. This is the standard form. This is just what your calculator can show you to 3 decimal place, but it's got to be to 3 decimal place. On to the next one, the same deal, but in one H2O, you have 2 hydrogen atoms. So the mass of hydrogen atoms is going to be 2 times 1, because out of the 18, 2 times 1 plus 16 is 18. There are 2 hydrogen atoms. Okay, so 2 divided by 18 times 0.144, I get 0.016. So that is in gram. There is 1, 2, and 3 decimal place. Now I want the mole of hydrogen atoms. So the mole of hydrogen atoms is mass over mR. So don't forget, always think about, is it atoms or is it molecule? So it's just divided by 1, which is just 0.016. Oops, not gram, but mole. Now use your answers to calculate the mass of oxygen present in A. So A has carbon, hydrogen, oxygen. I have the mass of carbon. I have the mass of hydrogen. They were what I calculated previously. Mass of carbon, mass of hydrogen, 0.096, 0.016. So this is 0.096 gram, and this is 0.016 gram. So what is the mass of oxygen? So I hope you can see that if your A consists of carbon, hydrogen, and oxygen only, if you have the mass of carbon, if you have the mass of hydrogen, you have 0.240 gram of A. So the mass of oxygen atoms is going to be the total mass, which is that 0.240 gram, 0.240 gram of A, which contain all these 3. Take away the mass of carbon, take away the mass of hydrogen, so you're going to end up with that mass of carbon. You add it with mass of hydrogen atoms, so 0.096 plus 0.016, I get 0.112, so 0.240 minus whatever is in the bracket, I get 0.128 gram, because this is mass. Now they want the mole of oxygen atoms, so the mole of oxygen atoms, I hope you can see where this question is leading to now. Mass over the atomic mass, 0.128 divided by 16. Again, this give me 8. Well, you can show the 1 to 3 decimal place, which is 0.008. If you want, you can express it to standard form, but you must show it to 3 decimal place as required by the question. Okay, so both of these will be correct as well, as long as they are to 3 decimal place as required by the question. Use your answers to A. Empirical formula. Empirical formula is the simplest ratio of atoms. Simplest ratio of atoms. So what we have is carbon, hydrogen, oxygen. What we have is mole. And mole of oxygen atom is 0.008. So I put in 0.008. Carbon, mole of carbon atoms is 0.008, and the other one is 0.016. So 0.016 for hydrogen, 0.008. Now you want the simplest ratio, because it's the simplest ratio of atoms. So you divide by the smallest number. then hopefully you can see very simple that it divide by itself is 1. This thing is 0.016 if I write properly, and you get 2. The simplest ratio is going to be 1 carbon, so I don't write the 1, it means there's 1, so it's CH2O. This is empirical formula, and this is not necessarily the molecular formula, it's just the simplest ratio of atoms in the compound, which is empirical formula. Alright, so that's it for this tutorial, and there are a couple of difficult questions, but it's not impossible to do. So I hope that has made sense to you on empirical and molecular formula. Click the button on the bottom right to subscribe to the channel, and yeah, do share the channel widely with all your friends, your chat and study groups, juniors and seniors from school, relative, and whoever else is doing the 14 to 18 years old chemistry. And of course, the 14 to 16 years old O-level or IGCSE chemistry students can just use the O-level or the IGCSE topical playlist on my channel for revision, as well as well, topical revision, I guess. Alright, so follow me at ptet.chemistry, ptet.chemistry on Instagram, Facebook, and Twitter to get connected, and yeah, just to get connected and ask questions and stuff. I'll see you in the next lecture tutorial. Thank you for watching.